Hello, and welcome to the Data Engineering Podcast, the show about modern data management. Data migrations are brutal. They drag on for months, sometimes years, burning through resources and crushing team morale. Datafold's AI-powered migration agent changes all that. Their unique combination of AI code translation and automated data validation has helped companies complete migrations up to 10 times faster than manual approaches. And they're so confident in their solution, they'll actually guarantee your timeline in writing. Ready to turn your year-long migration into weeks? Visit dataengineeringpodcast.com/datafolds today for the details. Your host is Tobias Macey, and today I'm interviewing Rajan Goyal about how to drastically improve efficiencies in data processing by reimagining the system architecture. So, Rajan, can you start by introducing yourself?
Sure. First of all, pleasure to be here, Tobias. Thank you for taking time. This is Rajan Goyal. I'm CEO and co-founder at an early stage data company, Datapelago. I am here in the Valley for last 30 plus years. This is my third startup, but we'll talk more about my journey. But happy to be here, Tobias.
And do you remember how you first got started working in data and why it has kept your attention for this long?
Yeah, well, it is a funny. My journey to data world has been unorthodox, I would say. My previous life, I used to build security systems like the network security, and then I went deep into the technology building processors, domain-specific processors, and or what's today buzzword is called accelerated computing. So, idea was to how do we make a specialized processors which are programmable and so on to do a specific function like security, deep packet inspection, and so on. So that was my previous life. We were building both MIPS and ARM based processors and were pretty successful, relatively speaking. And just before this, we put our hands on the data processing problem. We were working on data movement problem, which is sounds boring, but all the modern cloud infrastructure today, Tobias, is built on that principle. You have this disaggregated architecture. If I may take 1 second, few seconds to explain that. If you look at AWS or Google or Azure, you as a user want to take a server of, you say, give me 32 cores, 4 drives, one GPU, 25 gig network, or some other variant. Guess what? There is no physical server that's queue. You are composing a software defined server on the fly from a disaggregated set of infrastructure. Right. So you have your CPU racks, your storage racks, your GPU racks, and drive racks, and then connected over high speed network. And then you're dynamically composing this SKU that you're looking for. So in my previous life, I was working on technologies to enable this modern infrastructure that we see today, we enjoy today at AWS or any public cloud. And in fact, AWS Nitro, if you're familiar with that, or for your audience, is built on some of the technology that I built in previous lives. So coming back to your question, so I have a spending more time on making the infrastructure data centers more efficient, how to move data efficiently between compute to compute or storage to compute and so on. So what occurred to me was with Mellanox, with NVIDIA, with my previous companies, all these companies have more or less solved the problem. Obviously, it has to continue to improve, but fundamentally solved. So I observed that the next problem bottleneck will be in the computation. Now you're able to move data. Let's actually process it. And there are two hills in the data processing, Tobias. One is taken by the AI data model training and inference, which is also data processing, but in a different way. And another is the data processing itself to prepare for AI or for our classic analytics. And that, I think, was left untouched to keep up with the shift in the infrastructure that was happening, which I was kind of fortunate to be part of my previous life. And hence my attention got to this, that, okay, this is it's a very well $180 billion market today. So it's a pretty large business. Problem is big. It's relevant. And why don't we apply ourselves to solve? That's how kind of a more bottom up engineering mind took me to this world of data. And ever since, it is fascinating. It's validating what we started with, but that's how we got in. I personally got into this world of data, coming from computing, storage, and networking world.
And digging into some of those hardware level capabilities and constraints, most people who are working in this space, they're going to be fairly familiar with the system architecture of their laptops or their desktops. So the von Neumann architecture, which has been prevalent for decades at this point. And as you mentioned, because of the requirements and the high throughput and the high scale of these data centers and the cloud providers, you mentioned that they have a slightly different way of composing those different pieces together to be able to give that flexibility. And I'm wondering, from your perspective and from the understanding that you've gathered from working in that space, how that fundamentally changes the ways that people need to be aware of the compute capabilities and how they link together versus the model that they're likely working from with that von Neumann approach that of the co-located CPU, RAM, disk, and just how that factors into the capabilities of actual data processing and data movement in those environments.
Yeah. So let's break your question into maybe three topics, if I may, okay, to give the proper context. The first is the classic idea of, I think Nutanix invented this word called hyperconverged. Idea was you put it in a single pizza box, if I may use that example, co-located your CPU, DRAM, storage, networking, and that's your becomes your cookie, and you kind of replicate it 1,000 times or 10,000 times, 100 times to get your scale out, right? That was the then came the model of disaggregated, not hyper, but disaggregated, but composable infrastructure that we just talked about that, right? Now, in that regard, now things are far apart. Obviously, networking has solved the problem to make it appear like low latency and so on. How do we not spend CPU cycles in that? But it is still not a co-located world. So now you have storage racks, compute racks, and so separate over network. The third shift, if I may, or next subsequent to that, is the compute itself is no longer homogeneous. The last decade, we as an industry spent time to everybody standardize on Intel or AMD x86 architecture, and you write software once, and Intel is supposed to do every 18 to 24 months, doubling the performance, and life is good, right? But that train has stopped. Moore's law has flattened, and you're not doubling the CPU performance every generation to generation. So what's next? Next step function is accelerated computing. Now you have this heterogeneous elements, CPUs, GPUs, FPGAs, TPUs. AWS has their own chips. Now you're not finding a homogeneous server. You're finding a heterogeneous server. So that's the reality in the infrastructure which is happening. So if you observe this and ask a question, if you are a now coming back to your overall theme, if this is the world we are born in, now if you are a data practitioner writing Python code or a PySpark code or writing SQL queries, you cannot be bothered by GPU kernels or FPGA programming, right? So how those people who are building this platform bridge that gap? That's where companies like Datapelago play that role to build intermediate layers between a Python programmer versus the underneath heterogeneous infrastructure that we are providing, that system in data centers are built around, what that stack should look like. That's kind of maybe high level view of how it should operate. So there are two ways. Now, one is the users of the data platform, one are the builders of the data platform. Like we are in our world, we are the building the data platforms using this infrastructure. But our goal should be that how do we make the same abstraction that people are used to today? If I have to tell a Python programmer how to write a CUDA kernel, it's not going to work, right? So how do we abstract it out a level that whatever the today's data scientist or business analyst or the actual people who are writing applications, that abstraction remains same, and we can hide this complexity with software modular layer is the new problem statement, right? And hence the Datapelago or other companies like us would want to bridge that gap that has emerged because of this shift in the underlying infrastructure, Tobias.
Another division in the data ecosystem is, well, there are several, but one is open versus closed, where you have these vertically integrated, closed, proprietary stacks in the form of your Redshift, Snowflake, BigQuery, systems like that. And so they're built specifically for a specific problem, and they're optimized because of the fact that they control the end-to-end use case, versus these open and composable stacks that have been gaining ground, especially in the past 3 to 4 years, of the data lakehouse architecture, which is an outgrowth of all of the work that came from Hadoop and a lot of the processing that happened there, and then these different offshoot projects. And now they've largely oriented around a handful of table formats that make it easier for the different compute engines to be able to execute to a specific target. So Iceberg, Hoodie, Delta Lake. And because of the fact that those are all evolving separately from each other, they're all developed by different teams. Coordination is done generally by loose consensus or very lengthy RFC and proposal processes. And I'm curious how you see the variance in terms of the capabilities and the evolution of those two ecosystems of these proprietary, vertically integrated systems versus these open and composable stacks, and how that affects the overall efficiency and capabilities of those systems.
First, let me answer this more fundamentally, Tobias. I told you just now that in my previous life, we did this disaggregation at infrastructure level, right? From hyperconverged to disaggregated architecture was exactly same paradigm, if you observe it, which is that instead of building a one hyperconverged server, where everything is integrated, storage, your drives, your processor, your memory, and network card, and whatever into one server. And then to take a disaggregated where you have storage separated from compute and compute separated from GPUs and so on, right? It's a very similar paradigm shift is happening here from using now your example, from Snowflake or a Redshift with a monolithic storage and execution engine to a disaggregated where you have your open table format based data lake versus an execution engine. I think that's a fundamental shift has to happen because one box does not fit for every org, right? So people need different kind of data formats, different data, different execution capability. So this disaggregation has to happen, right? And that's what industry kind of went and did all that. So that's already acceptable norm. Even let's call them the converged architecture or like Redshift or Snowflake, they're also embracing Iceberg or using external tables and using open table format. So that's already happening there, right? Now, what it enables is that now, once you are in this new paradigm, now the best engine should win because you as an enterprise leave your data once into your data lake wrapped around your choice of open table format or otherwise. Now you want to have your choice of engine. So there is no vendor lock-in, right? Whether it's a proprietary or whether it's an open source. That's a fundamental architectural enabling, which is it's enabling is that you can have your own engine. Whether it's an open source or proprietary is different part, but at least architecture allows you as an enterprise pick the engine of your choice. That's one part. The second part is obviously even in this lakehouse paradigm, Tobias, you will see some are open source engines like Spark or Trino, and there are some closed source or proprietary, even Databricks, right? They are not pushing back their improvements in performance back to open source. So you will have a open source and closed source choices with rightfully so. Some are better performance and have premium, so that's a business decision. But architecturally, you would have those. So in both cases, but where open source plays a role is that standards, open table formats, connectors, file formats, what kind of connectors you use on the SQL side or whatever, right? So those, if you open it up, then this paradigm has long legs so that's kind of one point. If I may extend my argument one more further, is that as the data like Snowflake or Redshift, they were designed for structured and table data when they were designed, right, for some other problem. But now data is shifting. So you want a different engine. So you don't want to be enforced or forced to ingest the data into existing data warehouse and then only process it. You have to have this external legs or external connectors to the data in a data lake. So it is bound to happen that you maybe build a specialized engine for processing unstructured data. Now, processing unstructured data requires totally different. It's like either you use models. It's no longer just joins and sort and filter, right? You may have to do model-based inference, model-based metadata extraction to process unstructured data. So the engine of that has to marry those two, past world and the new world, right? So hence, I'm a full supporter, and I think it's going to enable a lot of innovation on the data formats, data engines, and the choice of the infrastructure required for each engine, rather than having a monolithic system there. So I kind of expanded your question, Tobias, but I think I gave you enough to cover the question as well. Yeah.
Absolutely. And on the point too of processing these unstructured data sources and the fact that we can't necessarily rely on these SQL engines that have been the heavy lifters for several years now, it makes me think that we're almost starting to drift back towards the MapReduce era of you have to write your custom code to turn through all of the data and hope that you got it right, because otherwise you're going to have to go back and start over, which thankfully we've gotten better at parallelizing that with systems like Ray and Spark and being able to get better efficiencies out of it. But we're no longer in the case where we have a single language target to be able to process the majority of data. We have these bespoke and fractal use cases and tool chains for being able to work with these unstructured data sources.
That's true. And I think there's a push and pull here, Tobias. There is a value in preserving the existing language because you have large users of that and they are familiar with that, and it is fine. So there is one dimension of this is to extend the language semantics as well as syntax to support this new operators, right? So that's kind of one dimension doing. Other is obviously people are using or want to use Python or some other just general purpose language to express your intent and do that. So I think it is still to be proven and seen where would we land once it's all settled. But I do see initiatives as value enabling existing user who's familiar with the SQL, for example, to be able to even have in the same. Because if you buy this argument of lakehouse with a single engine with a unified data store, and you say that you want to have a unstructured data semi-structured, there is a value in preserving the northbound API. Right, so that from that user it sees like two layers and I can use it, but obviously it will take time to get there. But the thing you mentioned, yes, for the Ray, having a flattened, if I may call it, distributed framework where you as a user can control what your app is doing and then use the power of Ray to just distribute it is a wonderful idea. But that's where you more power from the user to how to write. But like SQL world gives you the power of planner and optimizer and so on, which is kind of maybe missing there that we are familiar in the data world. But yes, I think it's still to be proven where language we will settle over time.
On the point of the overall ecosystem, particularly for these disaggregated stacks, having to do a lot of process and coordination to be able to make any step changes in capabilities. For instance, if you were to introduce a new table format today, it would probably be 2 to 5 years before it was actually usable in all of the different processing engines that someone might want to work with. So, for instance, Iceberg support for that landed in Spark initially, and then there was some initial support in Trino for a while, as well as a lot of investment in Dremio, etc. If you were to, so the Lance table format is another example where that is a newcomer and it's starting to be worked on to incorporate it into Trino and some of these other different engines. And because of the fact that it can take so long for these new capabilities to be broadly available to different people without necessarily having to bring in a completely different tool chain or re-architect their data stack, I'm curious what you see as the points of highest leverage in that ecosystem of disaggregated systems to be able to have the broadest change and the fastest capability of adoption without having to do that re-architecting and re-implementation.
I think there are fundamentally, which is what we just talked in the previous question, is that there is a merit to standardize the interfaces. And open table format is one of that interface. How do you deal with your data, right? So there is the more we standardize on it and agree on one format, better it is for the engines to take advantage. That's one part. But I guess there are two dimensions in which, in this context, the status quo will be challenged. One is the efficiency part, if whether that current format is better or efficient, and the second is for the applications, right, for the different application data patterns, access patterns for the data. And second is as the data is changing, because today's file form, the table formats are more for structured data, but as the data is changing to other multi-model unstructured data, what is that abstraction, right? How do we make that as a more common format is to be evolved. So it will evolve, but I don't think fundamentally it's going to disturb the relationship between the engine and the data, right? So that's how we see it. But from my point of view personally, and the where my expertise lies, is that the format plays certain role in the overall system's performance or efficiency, right? At certain point, it's good enough. Now you would want to focus on the execution side and the data processing and take advantage of the new infrastructure. That's where we are focused on, right? So that we leverage whatever the industry will lead us to from the file format point of view, we will support it. But let's focus on the execution side, because if you look at the enterprise bill cost of goods, you are paying 60 to 80% of the compute, right? Not so much on the storage or not so much on the networking. So the compute is where your bulk of the spending is, from energy and the cost point of view. And as the data is getting more and more complex, it is going to be more and more difficult or more acute problem to optimize. And that's where we are focused on, is how do we make the compute part of the data processing more efficient while still leveraging all these initiatives in the open table formats and so on.
One of the outgrowths of the past 3 to 4 years in the broader data ecosystem that I think gives a much better point of integration to have a broad impact as well is the broad adoption of the Arrow ecosystem for data interoperability. And when I was looking through the documentation for your site, I also saw that you hook into or at least support the Apache Gluten project, which to my understanding is a marriage of the Spark execution and orchestration system with the high performance libraries from, I believe, ClickHouse and similar systems. And so digging now into what you're building at Datapelago, I'm just wondering if you can talk to what was the point at which you decided that this was the problem that you wanted to solve, and maybe some of the strategy that you've developed around how to actually tackle that problem.
Yeah, first is the in-memory format, like Arrow data structure, or now the corresponding engine has its own place for efficiency point of view. But now we are in a world where it's as I said, heterogeneous computing. You use GPUs and FPGAs. Will the same in-memory format sufficient to extend hardware software co-design? We have at Datapelago, we have relooked it and extended that. So that's kind of one part of the problem. And the second one is that, regarding gluten or other technologies, Spark is a wonderful and extensible distributed framework, but it was designed with its own engine, which was written in Java virtual machine execution engine. So what gluten allows you to do is that, using my previous life analogy from networking world, where you had people used to build monolithic routers, Tobias, right? You would have a control plane and a data plane monolithic, right? So it's a very similar analogy in my mind, that how do you separate the control plane of Spark from its data plane, which is execution engine, and gluten plays that role to be able to punch the holes in both sides so that you can plug in your choice of execution engine as the backend, right? Think of like that. So that's a value that gluten. Now, given those two clarification or the context about what it does, our strategy as well as the vision has been is that what's the gap in the industry? The gap in the industry is that the data engines or the data platforms that we are talking about were written 10 years back when infrastructure looked different. Now infrastructure is changing underneath. So what do? Either you say, oh, I'm going to reinvent new Spark, which is for this new world, but you have this whole existing applications and workloads written for Spark. What about that, right? So then you have to figure out a way to insert the benefits of this accelerated computing to this existing ecosystem, right? That's the view Datapelago took. And hence, many of the techniques I have mentioned, some we have not actually publicly mentioned, is to service that. Where our view is that you build if I now tie all the points we have talked, so the world in our mind looks like following. You have a unified data lake. You store all your structured, unstructured, semi-structured data there. You have a universal data processing engine, which is what we are building. And it runs on the modern infrastructure. It handles any data. And on top, which is more important, it enables any data engine written in the past to take benefits of new hardware and the new data, right? That's the view we take. And then Gluten and many other technologies that we have internally developed as well as using open source enable us to fulfill that vision of that, so that we are not inventing Spark, we are not reinventing Trino. We want to give the benefit of accelerated computing to existing frameworks. So that's what, hence we have carved out this, what we call universal data processing engine, to give benefits. So that's our view, Tobias, how we look at it. There have been attempts in the past where people built their own SQL engine, their own GPU powered or FPGA powered, right? So my personal view is that the success of those attempts were not because GPU was not good enough or FPGA was not good enough. I think this last one that I just mentioned was one of the reasons why adoption was not there or was there. Because if you don't have a friction to insertion, then people can embrace the technology. And given how enterprises are already spending millions of dollars with thousands of users writing code, it will be kind of a non-starter to suggest, okay, now I have another engine. Can you learn again and let's stand it up, right? So that transition, that migration is not easy in that case, right? So hence the way we are doing at Datapelago is to not disrupt the North APIs, if I may use that term. So the users are using whatever they are comfortable with, but still give the benefit of accelerated commuting them. And Lakehouse paradigm has a big role to play, because if that separation had not happened by separating the table, or excuse me, data in data lake with the execution engine of your choice, we would not have been able to innovate the way. So there are a lot of past wonderful work on which we are you are leveraging and standing on that.
For people who are looking to bring in the Datapelago capabilities, they're already running a Trino or a Spark. What does that integration path look like, particularly if they're running those systems via some sort of vendor like a Databricks or a Starburst?
So let me, so I mean, we have not announced the product yet, but let me generalize it, right? Obviously, we have customers who are using it, but the idea is that let's first stay in the open source world, even though technology is applicable to any engine built with this paradigm. But idea is that, can you think about a sidecar or a training wheel attached to existing car or existing whatever analogy you want to put in, right? So that's what, think of like Datapelago UDPE is that sidecar or that accelerated wheels which you attach to existing clusters. Now, if I may use the word existing Spark, you attach that, and now all of a sudden your same workloads run faster, and they underneath it consumes the newer breed of servers available in the cloud. There is no need for hardware introduction or whatever. AWS, GCP, Azure, many other clouds have a lot of choices of servers with a very good price performance points, which have those accelerated computing instances, I call. When I say accelerated computing instances, I meant GPUs or from AMD or NVIDIA, from Tesla T4 to higher end and so on, and or FPGAs, and going forward TPU. So there are plenty of choices there. User doesn't need to worry about it, right? So our software, our technology handles it. What is the right computing element to use? That's one part of the problem. But most importantly, insertion is, you just, when you create a cluster or something, you point to our binary or whatever you want to call it, and then magically the system just shrinks size wise but runs faster, right? So that's how we insert. Let me pause here, Tobias. You should ask question if we need further clarity on this one.
No, that's definitely very useful. And to your point, the selection of which compute unit to use is definitely one that, as somebody who is writing a SQL query or writing some sort of processing logic for the unstructured data that I want to do some entity extraction on, I don't want to have to think about that level of detail. And so being able to just say, I want this to work, and then it gets federated out to the appropriate compute unit. And then obviously there are also questions around data gravity, making sure that those compute units are situated appropriately closely to the actual storage media. And particularly in that space of structured versus semi-structured versus unstructured data, where you do have those differences in language interface, I'm wondering how the work that you're doing at the point that it gets to your layer, is it largely just an intermediate representation because you've already been abstracted away from the specifics of the language runtime, and you're looking at some sort of intermediate representation at that point? Or is there some other translation that you're doing from the query language and the execution plan into being able to say, okay, I'm dealing with unstructured data over here, so I need to do these different compute operations, versus I'm running a SQL query, so I know I'm going to be dealing with Parquet files or JSON data for over here? Just curious about some of the ways that you're thinking about that problem as well, of being able to the end user, unify the differentiation between those data sources so that they don't have to think about where they're integrating your product.
Yeah, good question. So yes, absolutely. First, it's in if you don't do the way I'm going to describe, I don't think it's going to fly. You would want to keep it away, this complexity of where to run which workload, right? Or what computing element to use. So you still, if you're writing in Python or a PySpark or SQL, you just continue to write as is. And it's a job of the underlying stack to figure out which computing element is the right element to do that. And you did mention a couple of the points. One is the data affinity, and the second is the right performance per dollar or performance per watt, whatever metric is the right processor to execute that. And many more things go into the mix for that algorithm to decide, let me run it here, because moving data, there are high level things. You want to move compute closer to data rather than to data to the compute. So there are high level principles you want to address, keep in mind while doing this kind of scheduling and runtime management of the resources to the operator. That's for sure required. And the second part is that when it comes to the handling the data types, as you asked, yes, absolutely correct. Let me call it the chaotic data. Like when it is more chaotic data than a structured data, you need a lot more energy to extract what you're looking out of that. And that, hence, the accelerated computing instances play a better role in terms of efficiency than a general purpose CPU for to process that chaotic data. That's one point. The second is that that's where all of these processors, Tobias, are Turing complete. So you can run anything on a CPU as well. It's going to functionally correct. But if you want to break the problem where it is the right computing element, maybe you can influence the gates into some FPGA to process JSON efficiently, to parse JSON efficiently, than doing it in a GPU. Maybe that's the right thing to do. Or if you're doing a PDF extraction, nowadays it's all done in the models. So there is no need to parse the PDF to do that. You can just run a model. So now that is better than a GPU. So depending upon your algorithm, depending upon your data type, that your choice of the engine or the computing element may change, right? And obviously data affinity and all the stuff that you also mentioned in your question are also into consideration. So hence and if it's well served for the industry and the user, if all that complexity is hidden from the end user. Otherwise we will be the adoption will be too slow, and it will break the system, right? So that's what companies like us are working hard to solve, that problem, that how do I re-express, if I may use the word, algorithm for this new machine, for the new animal that is handed to us, right? That's what we do. And if I may quote Jensen Huang, NVIDIA CEO, he called it insanely hard problem, right? Because we are not in a world where you are handed over 100 gigahertz processor and recompile the software for that. Right now you have to rethink about, okay, I'm doing this new sort, or I need a new JSON parsing or a new PDF extraction. How do I re-express that algorithm for the new target machine is the problem. And all that is buried and deeply integrated into the underlying stack. Like in case of Datapelago, we build, but I'm sure many other companies are also working to solve that problem.
And so, if I can be a little bit reductive to summarize sort of what you're doing, the way I'm thinking about it is that it's analogous to being the LLVM for data compute.
Yeah, I mean that's a that's a big high bar, if you may get there. But yes, I would put it in a way that, yeah, I mean that's a good way to put it also. But maybe there's a simpler analogy I can mention. But yeah, we can leave it at that, Tobias. That makes sense.
As you mentioned, LLVM, that is a high bar. It has had a lot of engineering time that has gone into it. It's being used in a number of different use cases. And as you mentioned, the problem that you're tackling is also, to quote you, insanely hard. And given that, I'm curious, what are some of those engineering challenges that you're tackling, some of the foundational computing elements that you're having to reconsider or try to look at in different angles to understand how best to actually approach the problem efficiently? And also, to tack on one last question to this run-on question, because of the fact that it is a very engineering heavy effort, I imagine that there is a lot of work that you have to do about how to think about marketing it to people, both for consumers as well as potential investors, to make sure that you're given the appropriate time and space to actually invest in that engineering effort.
Yeah, makes sense. So let's tackle the last one first, right? Yes, it's like I'm using your light to shine, like where to go. So you have taken me pretty deep into the stack, and hence the technology details comes out. Okay, so but otherwise, you're right. From user perspective, investors perspective, we would want to make it as simple, as frictionless to insert and understand. And that's what is the whole UDP idea, accelerating Spark or Trino without changing the application, with the thing we just talked, enables us to do so. So all these complexities and the what we just talked about are inside our stack, inside the software, not visible to the user, right? So whether it's a choice of the hardware, whether it is a choice of the size of the cluster, whether where to schedule what, and how to break algorithms, this is all done by our software, right? So nothing is visible to the user. The second part is that what you meant in the big first part of the question was, what are those complexities, the challenges we are solving? One we just touched about is re-expressing your algorithm for this new primitives that computing element we are offered. So that's one part. The second part is also that it is a large distributed systems problem, Tobias, and there's something called Amdahl's law, right? If you focus on a one function to accelerate, and if that function is only used fraction of the time, you will only get the portion of that fraction accelerated from overall impact of the from the value proposition point of view, right? So you need to be very, very careful about the Amdahl's law, that you're not spending energy on a small portion of the workload, right? So in the distributed systems, it's the IO, it's the data movement from storage to compute, compute to compute, and even within a node, data movement from your memory or drives to the CPU. And then now when we're talking about CPU and GPU, you're moving data from CPU over PCI to the GPU and back, right? So those are all the flashpoints or hotspots. You have to be very, very careful and design a system which is impedance match between compute as well as IO, right? It's a pretty complicated, sophisticated distributed systems, not again to scare the audience or the user, but this is all done underneath by the software to A, pick the right computing element, B, pick the right algorithm to write on run on that algorithm, and C, to build a impedance match distributed system so that the user is able to get the value out of it. That's what makes this problem insanely hard, right? All these three things that we just talked. And the fourth thing is to make it appear to the user as if nothing has changed. That makes it even more exponentially more harder. But as we were talking about this meta concepts of lake house, open table formats, separation of compute from storage, gluten, all those things have enabled us to realize our vision, right? But to make it seamless from the user point of view. But there is no escape from solving the three things that I just told you. Fundamentally, you have to solve it. Otherwise, it's not going to give the value that the potential that this new architecture has, right? I hope this is clear to me.
Absolutely. And as you're talking as well about the distributed systems nature of the problem, the fact that you have to impedance match the compute with the IO capabilities, it also brings in the question of what are those low-level storage primitives that you're working with, especially because of the fact that it sounds like you aren't in a position to be able to standardize that or enforce that because you're just processing on already existing data. So it's not like you're building a full database system and you can decide between an LSTM or, copy on write versus merge on read, et cetera, et cetera. So you have to work with the data as it already exists across that wide variety of different storage approaches and be able to process them as efficiently as possible.
That's correct. Yes, I think the industry has already, let me say this way, willing to pay the price of disaggregating and getting away with this proprietary control structures to wrap the data around, right? So there is a penalty you pay for that. But the trade-off is now you have separated and you have disaggregated, and that's a more architectural knob which is have more benefits, right? So that is already realized. People are willing to pay that cost. Where we come into the picture is, okay, you are already in deficit because of that departure from that monolithic architecture to this disaggregated architecture. How do we bridge that gap and even make it better? And hence what we just went over the discussion, this accelerated computing, having impedance match and all those things enables us to not only cover the deficit but also make it future proof as the data size grows, as the computing capability improves. So that's the how I look at it, right? But you're right that starting point is that we don't have luxury to store data which is more friendlier to us, and we don't want to do that. That's when the vendor lock-in comes in. Enterprises don't want that, right? They want to have a freedom of store once and use as many times. And if I'm storing a proprietary format suitable for one engine, now you're locked in by definition to that engine, right? That is a okay compromise as long as we are able to deliver on the promise of this thing, right? Hence, I think this accelerated computing plays a big role in realizing the overall vision of Lakehouse, this separation. Otherwise, that deficit will become so huge that people would ignore the future, but at least solve today's. And pendulum may shift back to the monolithic because it's not delivering on the promise, right? So I think we may have some role in enabling this vision and making it more future proof. We meaning in the using accelerated computing and the things that we just talked about in our humble way. Yeah.
And in terms of the impact on behavior and prioritization for teams who are working with these data lakehouse systems, where today they maybe are trying to run a Trino cluster, they execute a query, it takes some number of seconds to execute because it's executing across hundreds of gigabytes or terabytes of data. So then they bring in Datapelago, and that drops from multiple seconds down to single seconds or sub-seconds, whatever the order of magnitude improvement is. And I'm curious how that shift in speed and efficiency and capabilities changes the ways that they think about what data to use for which problems.
Yeah, I think there is a certain angle to this, right? Right now, the way business model is, you're always paying as a consumption of something. So you are paying as a consumption of compute resources. If you make shrink that, that directly translates to your TCO savings, right? So that's what unless you're charging your premium, which many companies do, but for the performance improvements and so on. But otherwise, fundamentally, the performance has a benefit of reducing your TCO. So that's one part I wanted to just address. I missed your second part, Tobias. Can you repeat the second half of the question? Yes.
So just wondering how the increase in speed and efficiency of that data processing changes the ways that teams think about what data to use for which problems, and how it maybe unlocks greater potential for bringing larger volumes of data to bear on the organizational challenges.
Right. So two parts to that. One is there's a business answer and there's a technical answer here. The business answer I hear from many CIOs is that your TCO savings that I have in my current workload and frees up my budget to do exploratory work that I would have not done otherwise. Okay, because they want to do AI processing or Gen AI or fine tuning or their RAG processing, just today's whatever is in the thing. So that is a business advantage of reducing your TCO in the current spend. That's one part. The second part is also that there are many use cases which we make practical, which were not viable earlier, right? Because now we are able to meet SLAs with this new architecture without needing to put it in a, let's say, proprietary data warehouse. If you can do that, then it enables many new use cases. So for example, in a telco world, we are involved with a company which they have to meet certain by morning or something, all the data ingested overnight need to be processed and be ready for the next time when it starts, right? Earlier, given the budget, they would have to cut short either on the quality of the processing or the amount of data they do, right? So that affects their relevance or be staying competitive in the next day. So hence this speed up and this extra volume of data or more deeper analysis you can do within the same time frame enables them to be more sharper and competitive next day. So that's a real use case that we are enabling that. But right now, given the current macroeconomics and otherwise, everybody's under stress, I would say, to reduce their TCO because, all said and done, this pay as you go model looks okay in the beginning, but moment you start using at scale, then the reality starts sinking in on the cost and so on, right? And that's kind of where many people are grappling, and our technologies that we built at building a Datapelago enables them to keep that fundamentally, right? We are not here playing a margin game that okay, if they are paying 10% savings here and we are fundamentally changing the price and the performance assumption, and in that case we enable them to reduce their TCO and help them scale as a telco example I gave you, or even free up the budget to do things which they want to do, but there is no budget, practically speaking.
In the work that you have done with some of your early customers and design partners, what are some of the most interesting or innovative or unexpected ways that you're seeing the capabilities that Datapelago unlocks applied to their business problems?
I think, to be honest, I will not have that many data points to generalize that, right? But so I will just caution with that, my next answer. But uh, you know, there are many, and we have not touched many verticals yet. Manufacturing, whether it is in cars or in semiconductor, in shop, factory, when there's so many sensors are generating data. So there are lots of use cases where efficiency, performance, latency reduction is important, and we will enable that, right? But right now, more or less, I think I can generalize that either the TCO savings, right, is important. Using that savings to increase their amount of data they process, and how it helps. That's one part. The second part is, which is also obvious now, in the machine learning or the data development, excuse me, the model development and model training workload specific, data scientist time is very important. And how much time they spend on processing data or preparing data is important, because it comes in the way of how iterative and how fast you can train models. So that's another area where we help and speed up the data pre-processing for model training, which translates to saving the data scientist time, and so on, right? So there are a few higher level values we see, but next time we talk, I can give you a little bit more better insights than that. Yeah.
And in your work of investing in this problem space and working at this layer of the technology stack, which sounds like is maybe even a little bit higher up than some of your previous companies, what are some of the most interesting or unexpected or challenging lessons that you've learned personally?
Well, you learn a lot, Tobias, especially, if I may, I don't know if this is the angle. I mean, first is, as a entrepreneur, as a CEO, or as a founder, it's a learning every day, right? It's, I say that you building a feature versus building a product and versus building a company is exponential scale complexity, right? So hence, it is a lot of learning technically. We are kind of breaking new ground every day, because many of the areas that we have to solve are some unsolved problems. How do you move data, or how do you process? Your data size is terabytes, your GPU memory is only 16 gigabyte. How do you manage that, right? So that's a technical problem to solve, and many more such things. So there are many technical problems to solve, to do what we do. Then there are many business model related problems to solve. How do we insert into user space without disrupting the ecosystem? That's another way to innovate. And then the obviously third is, it's a fast evolving market, a problem space itself. Data types are changing, and so on. How do you build an architecture which has legs for future proofing? So there are a lot of areas which we are learning, and I'm personally learning daily while working on this problem.
And for people who are looking for ways to increase the efficiency and speed and flexibility of their data systems, what are the cases where Datapelago is the wrong choice and won't have the impact that they're hoping for?
I think, one is a fundamental answer, right? One is that if you are, as I said, that our first attempt is to do an impedance match between data movement and compute. And if computation is the bottleneck, we will free it up and make it. That's a little bit fundamental answer I'm giving you to Tobias, right? So if you find a workload where you're processing very less, but you're just moving data or moving things here and there, probably there's not much for a GPU to play a role in that, right? So that's kind of a fundamental answer to that. But I guess, I would not give up like too early in that journey, because we are still evolving, and solving. So, but right now, yes, if I were to put it today's state of the art from Datapelago, we look for, when you're processing complex data, you're spending a lot of compute cycles to do it, and there is a data movement from your storage to thing, but relative to that, you're spending a lot more on the compute. That's the higher level, um, highest order bit, I would say, to resolve, to see where Datapelago will be applicable, right? Because we are attacking the computation part of the problem, more than that. We are trying to be, or we are efficient in selecting how to move data efficiently, sure. How to, I mean, there are many data techniques to do dynamic filtering or row group based pruning in Parquet or whatnot, right? Like, so that you're very, very selective in only reading data that you need. And those are complementary techniques to us. But once that is done, and even then, if you are reading too much data, then and the ratio of the IO to compute is disturbed, and then there is not much probably data to add value right now, right? In my previous life, we have solved the data moment problem, but now in context data, it's a computational problem we're solving.
As you continue to build and invest in and move towards general availability of the technology that you're building at Datapelago, what are some of the capabilities or specific projects that you're excited to dig into, or any of the features that you're building towards?
Yeah, it is the good news or the bad news, however you want to take it. It's an endless world, right? So why is it endless world? So let me share a few dimensions, right, in which we want to and we will go. One is the world of data platforms itself. You handle Spark, you handle Trino, then there are many more which can benefit from this accelerated computing. So that's kind of one dimension. The second is the data types itself, right? So data types are changing from multimodal and unstructured, semi-structured data, and the kind of computation you do, kind of models you want to bring in there, is another dimension where the platform will evolve, right? And the third is applications itself. Because now different, what is your distributed framework? Is it a Ray or is it a Spark? What kind of, so that is another dimension to go. Fourth could be multi-cloud, which is obvious from hybrid on-prem to that. But now there is this new wave of GPU clouds emerging, right? How about we address data processing there? So there are many, many dimensions ahead of us, Tobias, to go and innovate, and many of them are in our roadmap, and we are actively working.
Are there any other aspects of the work that you're doing at Datapelago, the specific problem of efficiencies in data lake architectures, and the overall evolution of data processing, particularly as generative AI brings unstructured data more into the forefront, that we didn't discuss yet that you would like to cover before we close out the show?
Not really. I think you covered pretty broad areas. I hope this is useful. But yes, we have not covered the how the data processing for generative AI world is evolving and so on. But we can save it for the next time. But yes, there is a very fascinating world emerging in front of us. Like obviously, data is changing, but the kind of data processing, which is a combination of, actually, I will leave this for you and your audience, which is that the two pipelines are also converging. People want to apply analytics primitives along with the unstructured data processing together, right? How does that world look like? Where you want to do joins as well as extract metadata from PDF, right? So that's a problem to be solved, and that's where I think the direction platforms will take. Like on a single platform, how do I do unified processing both for structured and unstructured data, right? That's the next frontier, I would call it, for us as well as in the industry.
For anybody who wants to get in touch with you and follow along with the work that you and your team are doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
What I can answer is that with the generative AI, there's a lot of innovation have to happen and already happening. How do you even use natural languages, for example, to express your intent, right? From natural language to SQL or natural language to Python or whatever, right? How do we express? And there are many initiatives in that. I think that is probably one area where industry will evolve and learn and improve to even make the interface easier so that even people who are not familiar with SQL, can you use your data platform for your other? So that's one area. But I'm sure world is full of smart people. They will think of something better than what I can contribute right now on that problem.
Absolutely. And everybody's always filling in different gaps which then expose other ones. So it's a very fractal problem space. So thank you very much for taking the time today to join me and share the work that you're doing at Datapelago and your insights into the fundamental challenges of data efficiency in these disaggregated architectures, both in the software and the hardware layers as we work in these cloud environments. Appreciate all the time and energy that you're putting into improving some of those efficiencies, and I hope you enjoy the rest of your day.
Thank you, Tobias. It was wonderful and a pleasure, and many of their questions were insightful, and I hope that it is useful for the audience. Yes, thank you for doing this.
Thank you for listening, and don't forget to check out our other shows. Podcast.net covers the Python language, its community, and the innovative ways it is being used. And the AI Engineering Podcast is your guide to the fast-moving world of building AI systems. Visit the site to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story.
And to help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.